Hi all, welcome to your Algebra 2 notes. We're going to take a little trip back in time. We're going to go to 7.2. We have graphing rational functions. So go ahead, draw yourself a set of axes because we are going to add a function to those family of functions that we've been working with, and we're going to add one more parent function to those. All right, so the one we are going to work with is f of x is equal to 1 over x. This is, of course, our parent function. Our rational function is what we call it. And if we start thinking about some values that we have, I'm just going to go ahead, I'm going to plug in 1. So 1, 1. When I plug in 2, I have 1 over 2, so a half. Then I come down to a third, all right? And then, but if we notice, if I actually go ahead and I plug in a half, I have 1 divided by a half, also known as 2. Plug in a third, so it gets really close. And the numbers actually start to get bigger and bigger as they become closer to 0. And that happens on the negative side as well. So it goes through the point -1, -1, -2, -a half, -a half, -2, and it creates this curve. You can go ahead and check it out on Desmos if you like, that gets super, super close to the x and y axes. And what we call that, when it gets super, super close to these x and y axes, is that we call them, of course, our asymptotes. So our parent function, one of the properties of it is that it has a vertical asymptote at x equals 0, and of course a horizontal at y equals 0, also known as your x and y axes. And if we want to go ahead, I just want to state our domain here is that x cannot be 0 in this case. All right. So this is actually what we call a hyperbola. I'm going to put that in a different color. Because it has these two sets of axes and it's going ahead and it's working really, really close in those two different directions. So it starts to mirror itself on these two sets of axes. So we're going to work, of course, from our parent function when we are graphing these. And you guys all know your transformations. So let's go ahead, when we're working with our transformations, we're still going to work with the same letters A, H, and K. So our same transformations. So for example, I'm going to go ahead and say y equals A, which would be our stretch, over x minus h, and you guys know h is your horizontal shift, plus k, which is your vertical shift. So if I go ahead and switch a color here, I know that this is my stretch, and when it's negative, it's of course reflected. And we'll switch over and call this my vertical. And the thing about my vertical shift is that it also happens to be my horizontal asymptote. So y equals k is also your horizontal asymptote. And if it is your horizontal asymptote for your vertical shift, this horizontal shift in here is your vertical asymptote. So we have x equals h for your vertical asymptote. So using these transformations, we are actually able to graph some of our functions. So when I'm talking about this one, I'm going to say example 1, that we need to go ahead and graph y equals 4 over x, put this in the middle, x minus 3 plus 1. So we're going to go ahead and graph this when we set up a set of axes here. I'm making mine pretty big because I want to make sure that we can see all of our shifts and everything on there. Okay, so I need to first set up my asymptotes. And with my asymptotes, I'm going to go ahead and I am going to look for my my vertical asymptote first, and I know that that's coming from this -3 right here. So we know that we go in the opposite direction. So we're going to go to 3 over, and this is going to be my vertical asymptote. Now I want to go ahead and I want to work with +1 for my horizontal one. So y equals 1. Here is my horizontal asymptote. Now I've put them in highlighter, but we usually do this with our dashed lines. Okay, so now that I know where my asymptotes are, and hopefully yours might have some dashed lines on there, I'm going to go ahead and I'm going to start graphing this. However, I need to be very careful with this stretch. So this stretch of 4 up here. And the stretch is a little bit different. I'm going to end up going over 4 and up 1. So I usually go over 1, up 1, but I end up going over 1, 2, 3, 4, up 1. And I'm also going to stretch it the other way. So I'm going to go over 1, up 4. So I have these points on here. All right, but here's kind of an interesting thing about these is that this point here in the middle of them ends up being the square root of a, or for us, this ends up being the square root of 4, also known as 2. So for us, it goes over 2, up 2. And from here, we are able to draw the first part of our rational function. And then, of course, it's the same thing with your negatives. So you end up having to go 1, 2, 3, 4, down 1, 1, 1, 2, 3, 4. This one in the middle ends up being a nice even number. And from there, you are able to go ahead and graph them, showing your asymptotes and showing the numbers that they go through. So it's pretty straightforward when you have your shifts on there for you. However, there are, of course, times when they are not available for you. So like this example, we have y is equal to 2x plus 3 over x plus 1. And I'm going to draw a set of axes. So this obviously is not in the same form of y equals a over x minus h plus k. So we need to go ahead and figure out what our asymptotes are from there. So this is actually what we call in the form y equals ax plus b over cx plus d. Now be careful, this a is not the same a that we're used to. It means a little bit of a different thing. Now, the cool thing about your vertical asymptote is that it actually is your domain. I'm going to switch colors for this one. So vertical asymptote is domain. And we know that our domain with these means that your denominator cannot be 0. So for us, we would know that cx plus d cannot be 0. Or if you want to go ahead and set that equal to 0, for us, when we have this one, I'm going to highlight it in blue for us, it's x plus 1, meaning that x plus 1 cannot be 0, minus 1, x cannot be negative 1. And we can go ahead and say that that's also x equals 1 is our asymptote. Sorry, negative 1. So we're going to go ahead and we're going to graph that asymptote here at x is equal to negative 1. It's a little bit different with our horizontal asymptote. And so the horizontal asymptote we actually find by taking a over c. It says y is equal to a over c. So for us on this one, we have to take 2 over, and c for us is 1. So y is equal to 2 over 1, also known as y is equal to 2. And I'm going to go ahead and graph that on our graph here. Okay, so now that you have your asymptotes, it's a really good idea to just go ahead and kind of start plugging in some points for your graph. The first one that I'm going to plug in is I'm actually going to plug in 0 because it's the next one over from my asymptote. So I have 2 times 0 is 0 plus 3 over 1. That ends up being 3, so I get to go up 3 right there. And that actually tells me that I don't have a stretch on this because I ended up going over 1, up 1. So I don't have a stretch. But if you wanted to go ahead and plug in some other points, you would see here that they end up being some nice values. Sorry, that one's not very good. That get really close to these asymptotes, and then of course you can mirror that on the other side. If you want to kind of prove it to yourself, you would be able to plug in some values. So for instance, if we plug in negative 2, we have 2 times negative 2 plus 3 over negative 2 plus 1. That ends up simplifying to 1. And if you didn't want to go ahead and graph it that way, you of course can always kind of change around your function. So you can change this function here. We're starting with y is equal to 2x plus 3 over x plus 1. And we can change it into y is equal to a over x minus h plus k. And how we do this is we want to think about it kind of like simplifying a fraction. So simplifying a fraction. And how we simplify a fraction is that we actually go ahead and we can divide. So I'm going to use synthetic division for this one. And I'm going to take this number right here. So this ends up being a negative 1. And I have a 2x plus 3. Oops, that's not what I have. I have a 2 and a 3. I'm going to bring down my first term to 2 times negative 1 is a negative 2. And then I have 1 as a remainder. And if I wanted to go ahead and I wanted to write this as a fraction, I would write it as 2 plus 1 over x plus 1. However, we don't write that. We kind of flip it around it the other way. So how we would actually write this one is y is equal to 1 over x plus 1 plus 2. And we can go ahead and we can kind of check some things off. And I want to say, hey, is my horizontal asymptote at positive 2? Yes, it is. What about that vertical asymptote at negative 1? It is. It doesn't have a stretch. So we can go ahead and kind of change that around. And the same thing is that I'm going to kind of add this note onto here, is that it is just like changing 17 over 5, and we're going to say that that would be equal to 3 over and 2/5, or if we wanted to put it in our new special way, 2/5 plus 3, it would be the same thing. So this is just like changing those fractions into a mixed number. And that's it for your graphing notes.